The science of modern astronomy tells us that most of the elements of which we and our planet are built were produced by stars. This graph shows crucial evidence that supports this idea. In this video, we'll discuss this graph and how it lends support to the idea that we are made from star stuff. The graph shows how the abundances of various elements in our galaxy compared to that of hydrogen. Recall that atomic number, shown on the horizontal axis, represents the number of protons in an atomic nucleus. Each atomic number corresponds to a different element of the periodic table. For example, atomic number 1 is hydrogen, atomic number 2 is helium, and atomic number 26 is iron. The vertical axis shows how the abundances of various elements in our galaxy compared to that of hydrogen. The abundance of hydrogen is therefore set as 1, since we are measuring other abundances relative to it. Notice that the first tick mark as we go down is labeled 10 to the minus 2, which is 1/100th, so if any element had this abundance value, it would mean there were 1% as many atoms of this element as atoms of hydrogen in the galaxy. The next tick mark is 10 to the minus 4, or 1/10,000th. Nitrogen is close to this value, telling us that there is one nitrogen atom for about every 10,000 hydrogen atoms in the galaxy. Elements with lower abundances are even rarer in the galaxy. Now consider this question. Helium is clearly the second most abundant element, but what is the third most abundant? Is it lithium, carbon, oxygen, neon, or iron? The answer is C, oxygen, because it has the third highest dot on the graph. Notice that its abundance is about 10 to the minus 3, or 1/1000th, telling us that the galaxy contains about 1,000 times as many hydrogen atoms as oxygen atoms. The fact that hydrogen and helium are the two most abundant elements is consistent with the idea that these two elements were produced in the Big Bang. Beyond that, the patterns on this graph allow us to test our models of how elements are made by stars. For example, the three elements with atomic numbers 3, 4, and 5 are extremely rare. From there, we see a pattern in which elements with even atomic numbers, such as carbon with atomic number 6, oxygen with atomic number 8, and neon with atomic number 10, are more abundant than the odd-numbered elements that come between them. Also notice the fairly steep drop-off in abundance for elements with more protons than iron and nickel. To begin making sense of these patterns, recall the way elements are forged in low-mass stars. Near the end of its life, the core of a low-mass star becomes hot enough to fuse helium. This reaction fuses 3 helium nuclei into 1 carbon nucleus, releasing energy in the process. The helium nuclei each have 2 protons and 2 neutrons, which means they have atomic number 2 and atomic mass 4. The carbon nucleus has 6 protons and 6 neutrons, for atomic number 6 and atomic mass 12. Because this fusion reaction converts atomic number 2 into atomic number 6, it essentially bypasses atomic numbers 3, 4, and 5, which is why those 3 elements are so rare. Low-mass stars die after their helium fusion stage, but the stronger gravity of high-mass stars allows their cores to reach temperatures high enough to fuse heavier elements. Models tell us that one set of reactions proceeds as helium nuclei fuse into successively heavier elements. For example, helium can fuse with carbon to make oxygen, with oxygen to make neon, with neon to make magnesium, and so on. Many other reactions also occur as the core temperature rises higher, but models indicate that some of the most common should include the fusion of carbon and oxygen to make silicon, 2 oxygens to make sulfur, and 2 silicons to make iron. Notice that all these relatively common reactions produce nuclei with even atomic numbers, which is why these elements are more common than the odd-numbered elements between them. The many fusion reactions begin successively in high-mass stars. Each time the core becomes depleted in the elements it is fusing, it shrinks and heats until it becomes hot enough for the next fusion reactions. Meanwhile, the prior type of fusion can continue in a shell surrounding the core. Near the end of its life, the high-mass core resembles an onion, with layer upon layer of shells fusing different elements. In the final stages of the star's life, iron piles up in the star's core. This marks the end for the star, because iron fusion requires energy input rather than releasing energy, which means it cannot help support the core against the crush of gravity. As discussed in your text, the iron core collapses catastrophically, becoming a ball of neutrons and generating the enormous release of energy that we observe as a supernova. The supernova ejects the overlying layers of the star into space, creating a supernova remnant like this one, the Crab Nebula. Supernova remnants therefore contain the elements forged inside stars, and measurements of their contents support models of element formation and the supernova process. Moreover, the fact that the major fusion reactions end with iron explains the steep drop-off in the abundances that occur beyond that. Elements heavier than iron form only through rarer processes, including reactions that occur during and subsequent to supernova explosions, and, perhaps, in rare events such as the mergers of neutron stars. To summarize, the observed abundances of the elements allow astronomers to test and validate models of how elements are produced by stars.